Welcome to this online class where we will be discussing the difference between series and parallel circuits. Now, when do we talk about series or parallel circuits? Well, when there is more than one resistance in the entire circuit. Could be multiple appliances hooked together, because in practical terms, if we have to go and make a separate circuit for every single device that we connect to our electricity network around the house, it would be a complete mess. There would be too many of them. So we have to look into different ways of how to connect different appliances to one another, and that difference is in a series or a parallel circuit. Now, it's easiest to just visualize this. This is what we refer to as a series circuit. Two resistances basically back to back in a single branch, in a single circuit. A parallel circuit has a certain point where the circuit splits up into two parallel branches, both of which will have current running through it. Now, it's not the first time we've been confronted with these two. In the previous chapter, we've discussed and we've learned that a voltage meter has to be connected in, and that was in a parallel circuit in this case. We already learned that way that if you connect something in a parallel circuit, the voltage between both branches would be the same. If it weren't, the voltage meter could not do its job, right? An amperage meter, if you wanted to measure the current, would have to be connected in a series circuit. Why? Because the current would have to be the same within the same branch. This is, like it says here, because in a series circuit, the current will be identical in the same branch, obviously, while the voltage, in this case, divides in a series circuit. In a parallel circuit, the situation is reversed. There, the voltage will be the same in both branches, but the current will not necessarily be the same. Now, in order to understand what is going on, I'm going to draw a few of these things onto my circuits, just so you can understand what is going on. Technically, when you have multiple of these resistances, you could replace them with a single virtual resistance, for lack of a better word, which will be called a replacement resistor. And you can use formulas and equations, etc. to calculate these. But in order to understand, let's first look at our series circuit. To show the difference, I've made some very basic and very simple circuits, both of which use two resistors, one of 12 ohms, and traditionally that's written in circuit, while the other one is 36 ohms. And we do the exact same thing for the parallel circuit. We make this one 12 and this one 36 in this case. Now, what will always happen is, if you have to look at what your current does, your current, symbol was I, will start at the positive pole, and then it will just, let's call this the total current in this case. It will start flowing from positive pole to the negative in this case. That's the same for both circuits. Nothing changes there. How much current will be created? Well, that depends on the resistance that is in the circuit, which is what we saw in the previous chapter. The previous chapter taught us Ohm's law, that said that the amount of current that is created is directly proportional to the voltage, but reversely proportional to the amount of resistance in your circuit. Things, however, get slightly more complicated in these situations because you've got more than one resistance. Now, the easiest one to understand is the one on top. If your electricity has to go in here, through this one, it basically has nowhere to go. The current that goes through the first one and the second one, in this case, we would traditionally call this one current 1 and current 2. would have to be the same, because it's all in the same branches. So when we look at things, your total current is the same as the current you have through resistance 1. It is the same that you have through resistance 2. It doesn't change. And you could continue this on and on and on, depending on how many resistances you have in a series circuit, in this case. However, looking at what happens here, your current will just flow until it comes to this point where it can split up. And we'll still be calling this current 1 and current 2. The difference is now the current has split up. It becomes divided. So if we want to write that down, your total current is essentially the sum of current 1 and current 2. So it just splits up into 2 parts. These parts will not be equal parts because the resistances between the top branch and the lower branch, they're not the same. Now, when we talk about resistances, you can sort of guess what's going on. You will have more current flowing through this branch than through this branch, the bottom one. Why? Well, because current tries to follow the easiest path to pass with the least resistance, so the majority of your current will flow through the top part, while the smaller part will flow through the bottom one. As soon as they reconnect here, however, you will have your total current again. So that's what we mean by current will be divided between the two. You can't do that in a series circuit. It has to be the same. However, when your current can't split up, your total voltage that you have will split up. A part of the voltage will be going to this resistor, and a part of the voltage will be going to this resistor. Now, how much of that voltage will go where? When you think about it, voltage is actually sort of the electrical drive, the pressure, the electrical pressure that has to push the electrons through. This resistor has a higher resistance, so will need more of that electrical pressure than this one. Meaning, in a series circuit, you will create a situation that your voltage will divide in 2 parts. Not equal parts, just 2 different parts. Or, if you had 3 series, 3 parts, 4 parts, and so on. So in this case, this one will receive the most current in total. Right. It was different in a parallel circuit. We know from our experience with a voltage meter that your electrical pressure, your voltage, will be the same in each and every branch in this case. And you can continue this on depending on how many branches you have. This sounds like a difficult thing to explain, but it isn't really. We have compared electrical current to water current in our previous chapter, and we said that water will not flow unless there is a difference in potential energy between 2 places. If you take 2 vats and you fill one of them almost to the top with virtually no water in the other one, there will be no water flow until you connect them with a pipe running at the bottom. As soon as those 2 are connected, your water will start flowing from high potential energy to low potential energy. In this case, what are we doing? We're connecting them with different tubes, different thicknesses of tube. Now, if you get a very thick tube, one with a large diameter, water will flow easily through it. We will be calling that, in our analogy, a low resistance, a thick tube. Whereas something with a high resistance will be a rather thin tube. Water will have a hard time passing through it. Now, if you take one vat and you first connect it, the first part of your connection is a really thick tube with very little resistance. Right? Water will flow easily through it. But then straight afterwards, you connect it with a very thin tube with a lot of resistance. That thin tube is going to have a very large impact. It's going to block a lot of the water flow. In fact, all of the resistance that you encounter in this situation, if you were to do that, the total resistance would just be the amount of resistance from tube 1 added to the amount of resistance of tube 2. You're just making it more difficult and more difficult for water to pass through as you connect more tubes in one line. It's quite different in a parallel circuit. In a parallel circuit, you would not be placing those tubes behind each other, but next to each other. You would create several holes in your vats to sort of connect them through. And something weird happens. Even if you take one big tube and you connect them, as soon as you add another one, even a smaller one, more water will be able to flow from one vat to the other. Something odd happens in this case. The more of these branches you create, the lower your total resistance will become. Because, if we use our water analogy, you'll just have more and more tubes for the water to pass through. Meaning, you have to use an equation that uses the reverse of all of these resistances. It would be the reverse of resistance 1, the reverse of resistance 2, and the reverse of resistance 3, 4, etc. as time goes on. Now, these are your standard equations that you use to calculate the series circuit and the parallel circuit. In our next video, we'll actually be using these numbers, these values that we've been given. Just remember, there's a weird thing that goes on here. If your current cannot divide, your voltage will. And if your current can divide, ironically, your voltage will remain the same between those two. Made a small mistake here. This should have been voltage 2, of course. Now, in order to use or explain this with our water analogy, if you take one vat filled up with water and you connect it with several tubes to another vat, every single tube will benefit from that water pressure, that difference in potential energy. It will be the same as long as you connect them at the same height level, the same height level in that one vat. They will benefit from the same amount of water pressure. In that same analogy, if you connect several branches to one voltage source in a parallel circuit, they will all benefit from that original voltage source, because that voltage is the potential energy between this point and this point in this situation here. So you will actually create identical voltage between those two. But it'll become more obvious in the next video when we do that. I'll see you then.